whenever you and I solve these sorts of problems, we're going to assume theoretical, fictional, air resistance-less scenario called freefall. So in your notes, freefall is going to have a really specific definition. Right? Its free body diagram is going to be nice and predictable. When we deal with freefall, this is going to be the special state where gravity is the only force. He was doing freefall inside this like giant vacuum chamber where weight, or the force due to gravity, is the only force. It means you are totally able to ignore air resistance. And if you can ignore drag or air resistance, that means that all objects fall at the same rate in freefall. Whether it's a bowling ball or a feather, right? Whether it is a pile of books or a coffee filter. In the freefall state, when there's no air resistance, all objects accelerate due to gravity at the same rate. Hey, and I think you know this. What is the rate supposed to be in theory? 9.8 meters per second. Right. So the acceleration in theory is supposed to be 9.8 meters per second squared, and direction. Direction is going to be down. The only reason your graphs were giving you positive values for acceleration is because you know how you took your motion detector and turned it upside down? That since you are measuring downward, you are getting positive accelerations, but let's put them in as negative because the acceleration due to gravity is down. Okay. I was telling someone this because like this doesn't make sense to some people. Your freefall, free body diagram of anything in this state always looks like just weight going down. So in number 4, 5, and 6 on the homework that's due Friday, where it asks like to draw a free body diagram of this thing in freefall, it's always just gravity force going down, no drag or air resistance anywhere on here. And since gravity is the only force acting down, and net force causes mass to accelerate, I would expect the acceleration to be in the downward direction because acceleration goes in the same direction as your net force. Right? So for free fall problems, like what do you do with it now that you've got this concept? Where I'm most likely going to use this is to do things like make velocity versus time graphs so I can figure out how fast is an object moving, its acceleration, and how far does it fall. So I'm going to give you like 2 examples of that, and then I'm going to circle back to air resistance. I'm normally not going to include air resistance in problems. We're normally just going to deal with it in theory, where it's just negative 9.8, because air resistance is tricky. Okay. So how would I use these facts? That gravity is the only force, that we're ignoring air resistance, that the acceleration is negative 9.8. I would normally use them to make some sort of like velocity versus time graph to determine my position, acceleration, velocity, all that good stuff, our main kinematics, motion quantities. Okay. So let's say I do an example, and I'm going to choose an example from your homework that was due today. You know that problem where you have an object that falls for 5 seconds? Right? It falls for 5 seconds, and it starts from rest. It falls due to gravity, so I'm going to put this like negative 9.8 here. And this gives a graph that makes it change velocity. It gets a more and more negative velocity every second of time that passes. So for the 5 seconds that our diver is falling towards the earth, which by the way is incredibly long. I'm pretty sure that as a diver diving into a pool that you would not want to fall this distance. I think this is above the world record for this. This means that my person would start at rest and fall faster and faster and faster in the negative direction every second. Every second, it goes 9.8 meters per second faster in the negative direction. So that at 5 seconds, they're going 49 meters per second down, which is something like, oh gosh, 80 miles an hour. Even if you're diving into water at 80 miles an hour, that's not going to be fun for you. The graph for this one, because this one is already from like the homework you already did, had a graph of 5 seconds of time and a final velocity of negative about 50 meters per second down. So let's call that negative 49. Velocity is here. The positive end of velocity is up there. I just have to draw it. This person's diving towards the earth and getting faster and faster and faster in the negative direction. If I want to figure out how far they fall when they're diving towards the water, how far is doing area under the curve? So how far do they fall in 5 seconds? I would take my little t-chart, draw my velocity versus time graph, and use that to get the area under the curve. Anything having to do with distance, height, position, use area under the curve to calculate displacement. So how far did my person fall? This is a triangle area. So I would do 1/2, a base of 5 seconds, a height of negative 49. So my person's gonna fall down just under 125 meters. Let me give you the actual number though. 122.5. So this homework is gonna still practice you doing like your graph making skills. It's still gonna practice area under the curve. It's still gonna practice like calculating acceleration from a slope. But the trick is the acceleration is always gonna be 9.8 so that you don't actually have to recalculate them. So in example 1, this problem is a drop problem. Object drop from rest, speeds up. What if I do one that goes slightly differently? Let's say I have an object that instead of dropping it from rest, what if I like shoot it up into the air like a rocket? All right. Unfortunately, our class doesn't like have rockets in the curriculum, but maybe we could make that happen if we find an extra time day. Let's say I have some sort of rocket and I fire it up into the air. A thing that people sometimes have trouble on when they do projectile problems is they're like, well, doesn't the applied force still exist when the object's moving upward? Actually, it doesn't. When you throw an object up into the air, once it leaves your hand, it's no longer being touched by you. Once all the air is out of the rocket, its inertia is keeping it going upward. So let's say I launch the rocket and it's got this initial velocity of, how about we make it positive 29.4 meters per second upward. All right. My rocket's gonna travel up, slow down because of gravity, and hit a special thing called the apex. At the apex of motion, its velocity goes to 0. Because gravity has acted against the direction of motion, think like the velocity is positive and the acceleration is negative, so it slows down, stops, and then speeds up. Goes faster and faster and faster in the negative direction until right before it hits the ground. This type of problem, I call it a symmetry problem. Unlike a drop problem, which starts from rest and accelerates in the negative direction, I call this a symmetry problem or a toss-up because it has two things symmetrical. Its velocities are symmetrical. Let's say I shoot this rocket up and it's going 29.4 meters per second up. I know right before it hits the ground, then it's going to be traveling negative 29.4 meters per second down. The velocities are symmetrical. So I'm going to put velocity up equals down. But also the times are symmetrical. If it takes 3 seconds to get the top, it'll take 3 seconds to come back down for 6 seconds total. Now, how am I getting that in my head for the times? Well, what I'm doing is I'm going back to this T-chart method. I know the initial velocity here was positive 29.4, and that gravity slows it down by 9.8 every second. So by 1 second, it's going 9.8 meters per second slower, which brings it down to 19.6. After 2 seconds, it's going 9.8 meters per second slower, so 9.8. And if I keep doing this, I'm going to stop when I see that final velocity match the initial velocity. This problem shows that it takes 3 seconds to get to the top, 3 seconds to fall back down, 6 seconds total. My graph for this is going to look symmetrical too. It'll have a positive part of the graph going upward, and a negative part of the graph that completely cancels it going downward. What you're going to do for homework is you're going to practice different free fall scenarios. Either a drop problem where it's dropped from rest and speeds up, like a penny dropped off the Empire State Building, or a toss-up problem, a problem that your velocity upward matches your velocity downward, so then you can figure out how long is it in the air for. If you're looking at these and you're like, yeah, but my results weren't like that. Yeah, but your results were in a room full of air. In a room full of air, you get air resistance. And unfortunately, we're not going to deal with air resistance mathematically. We're pretty much just going to deal with air resistance like qualitatively. Describe in words, not calculations. So free fall in theory is where you have no air resistance. You have an object that's in a vacuum, no air. But in real life, the type that we won't deal with in problem solving, in real life, the presence of air means that you're going to have air resistance or drag. Air resistance is going to act against your direction of motion. So against the direction of velocity. And for a falling object, that might mean drag pulling up almost completely cancels the weight pulling down. If you were a person that had the trial with the coffee filters, do you remember how your object weighs like about 1 gram? Since your object weighs only about 1 gram, its weight is really, really tiny. Right? The weight for a coffee filter is only something like 0.01 newtons-ish. So if you have a drag that's almost about the same, these two mostly cancel. You're still going to get an acceleration down. It's just not going to be 9.8 anymore. So if in your lab you're like, my acceleration wasn't close to 9.8, it's because this is a room full of air and you have objects that have air resistance, right? Things that affect air resistance would be like the shape, size, and surface of your object. So that's what I was trying to do with the comparing basketball and bowling ball. I wanted something with about the same shape, about the same size. Surface is like surface material, so I can't really correct that. I can't really go smooth out a basketball. That'd be kind of a weird thing to try and do. All right. Since the shape, size, and surface material are about the same for a basketball and bowling ball, they have about the same drag, so about the same difference in their little air resistance properties. So we've got like 3 minutes left. If your group has to like still sort things out on the lab, keep in mind when I see you whatever your next class is. When I see you for whenever your next class is, then we're gonna give you a little extra time to work on your lab. I will also show you a workaround. So if you're not a big fan of doing this graph method, there is another way.